We're going to take a few minutes now and discuss vectors. We're going to start by looking at the idea of vector addition. If you remember, when we talked a little bit and read some about vectors in the past, we can represent a vector by an arrow or array. If we have vector A and we have vector B, we can think about them as being two arrows, and graphically we can represent them and add them by using what is sometimes referred to as the tip-to-tail method, where the beginning of one vector happens at the ending of another. In other words, the tail of one is at the tip of another. Notice that I use the half arrow typically over top of the letter designation to represent a vector. The end result is called the resultant, and that's what you get out from correctly adding vectors. In using the tip-to-tail method, it's simply then a vector that is drawn from the beginning of the first vector to the end of the second, and it can be used for any number of vectors added together graphically. The parallelogram method, notice I kind of paused there to emphasize the parallel aspect. If you have two vectors, A and B, and you draw them so that they begin at the same point, you can then complete a parallelogram by drawing the necessary parallel sides to the parallelogram, and the diagonal is the result. Unfortunately, graphical analysis of vectors usually will result in an approximate answer, and therefore we're going to tend to do things more algebraically. So let's look at this one-dimensional example. A seagull flies at a velocity of 9 meters per second straight into a wind. We're going to assume that the seagull is flying to the right, and I'm going to let this be VB. If it's flying into the wind would then be going the other direction, and I'm going to let that be VW. It takes the bird 20 minutes to travel 6 kilometers. Now, the resultant, which I'm going to call VR, in a one-dimensional case is simply going to be VB plus VW. In two dimensions you can't get by quite this easily, but in one dimension it's simply adding them. Now, if we're talking about the resultant, or VR, we know that overall the bird travels 6 kilometers in 20 minutes. So we remember that a velocity is simply a displacement per time. In this case, the displacement is 6 kilometers or 6,000 meters in a time of 20 minutes, which is 20 times 60 seconds. So we have 6,000 meters divided by 1,200 seconds, which is equal to 5 meters per second. I looked at that wrong. It says 5.00. Okay. Now, if VR is equal to VB plus VW, then 5 is equal to 9. We know that is the speed of the bird plus VW. So we now know that VW must be a negative 4 meters per second. The negative here simply means that it's going to in the opposite direction from the bird. Since we chose the bird going to the right, then the wind is going to the left. On the other hand, if we look at how long it would take the bird going in the other direction, we now know that for the other direction, we still have VR equal to VB plus VW. But now the bird's going to the left. The wind is also to the left, so that the resultant is 13 meters per second to the left. We can then find the time, because this is going to be equal to a negative 6,000 meters, because now it's going to the left, over our time. And so our time is going to be a positive, otherwise we have a problem at negative time. 461.5. We have 3 significant digits, so 462 seconds, which is the same thing as 7.69 minutes as opposed to 20 minutes. All right, how does the wind affect the total round trip compared to what it would be like with no wind? Well, the total round trip time with wind, a round trip is 20 plus 7.69 minutes, or 27.69 minutes. Without wind, you've got 12 kilometers divided by 9 meters per second, or 13.33. This is meters and this is meters per second, or 1,300 roughly seconds. Dividing that into by 60 to get minutes gives us 22.2 minutes. So what it's done is it effectively has increased the time for the trip by about 5 minutes for the bird. If you multiply a vector by a scalar, so let's say that we have something that looks like this. If we have the vector A, then 3A is essentially adding 2 more versions of A exactly in line in the tip to tail style. If we were to look at vectors as components, and we'll get more into components in a little bit. So if we were to double the components of each vector, so that we now multiply each of these terms by 2, 2u is equal to 2 times 1i plus 2j, minus 2j plus k. Now notice that I've changed the notation. Sometimes in print you will see vectors with bold print. It's not something you can really handwrite. What we often do is we use in print bold. Often in writing you will see these types of things. Okay? Or you will see these types of things. Okay? These things right here we will talk about in a few minutes a little bit more when we talk more algebraically. But essentially all you have to do then is do a scalar multiplication, and I'm doing the good old distributive property. So I have 2 of these, I have 2 times 2 or 4 of these, and I have 2 of these. And you could apply that to the other 2 examples just the same way.